Hi everyone, I'm really pleased to be following this fantastic lineup of speakers to talk about using naturalistic paradigms to understand language processing. Our focus is looking at language processing and language disorder in post-stroke aphasia. Just to get the slide out of the way, as we've been saying this morning, in recent years there has been a growing movement in the cognitive neurosciences field to be using naturalistic paradigms to study brain function under ecological conditions. Our work has focused on the development and testing of naturalistic tasks that reduce language demands, such as language production, while evaluating the nature of language processing. We're also setting up these tasks to examine discourse language processing and production that are more naturalistic than most fMRI tasks that we can do, which are limited to naming and reading. As I mentioned, we are really trying to do this with the focus on post-stroke aphasia while comparing them to healthy controls. So I'm going to talk about two studies today that are very different. In the first study, I'm going to talk about our efforts to characterize functional activity and connectivity differences during language processing in the language network as well as the multiple demand network in patients and their controls. The goal of this project broadly is to look at the role of the language network during language processing in people with post-stroke aphasia. And of course, they have a stroke in these regions, so they don't process as well. And hence, we're also trying to look at the role of the multiple demand network, which includes other regions, as they're processing language and using designs. So the hypothesis here is that patients with aphasia will recruit these MD, these multiple demand regions, as a compensatory mechanism to process language after a stroke. So they actually end up showing more activity in the multiple demand network during language processing, as well as higher connectivity between the MD and the language network, as well as within the MD network. For this work, we have scanned 31 individuals with chronic post-stroke aphasia. There are 27 men in this group. Mean age is 58 years, and they're all fairly post out their stroke, so 7 years. And we also have 33 age-matched controls in this group. So what these subjects do is they go into the MRI scanner and we collect structural data from them, as well as have them do a set of functional tasks that I'm going to have to describe them a bit more in detail. The goal is to identify language network in these individuals, as well as to localize the multiple demand network. And the way we do this is a series of steps. So first, they perform specific tasks that localize language function. So they're either doing a listening task where they're listening to intact speech or an unintelligible speech, or they're doing a reading task where they're either reading sentences or non-words. And this is expected to isolate language processing in these language regions of the brain. They also do a multiple demand task, which is essentially an arithmetic task where they have to do a simple addition or a hard addition, and the goal here is to identify areas of the brain that are involved in multiple demands, is cognitively demanding tasks, these are not language networks. And then there's a key methodological component here that's important, because once they complete these localizer tasks for each individual subjects, you identify the functional activation for that specific contrast, and then you average across subjects, you average the functional activation across subjects. And then you compare it to a probabilistic map of what healthy adults have already shown activation for. So for the language network, this includes 220 healthy participants. And for the multiple demand networks, this includes 197 healthy participants. So then we have, the way this gets done is the participant goes into the scanner, we correct a structural scan, figure out where the lesion for that person is, and then collect the functional scan. In this case, they're doing a reading task, count the lesion there as well, go through this first level analysis for a language task. So here we're looking at the contrast between sentences and non-words. And then from that, we extract the subject-specific ROIs that are cross-validated across runs, and these are constrained within these language parcels that I just described. So the key thing here is that for every given individual, the top to 10% response in subject-specific language functional ROIs are identified, and those become that person's contrast. And then when it comes to the naturalistic tasks, the subjects also complete a resting state fMRI where they're closing their eyes for 5 minutes, and they're listening to a story for 5 minutes with some questions at the end, and I'll just play
At
the
10
story
years
for you
old, I
now.
could not figure out what it was that this Elvis Presley guy had that the rest of us boys did not have. He seemed to me no different from the rest of us. He was simply a man who had a head, 2 arms, and 2 legs. It must have been something pretty superlative that he had hidden away, because he had every young girl at the orphanage wrapped around his little finger. At about 9 o'clock on Saturday morning, I figured a good solution was to ask Eugene Carruthers, who was one of the older and smarter boys, what it was that made this Elvis guy so special.
So they listen to the story, and then they have to answer questions after that.
At 10 years old,
And then we also had them do a silent movie watching task, where they either watch a video like The Cloudy or a 6-minute video, Presto. But I won't talk about that today because I'll talk about it in a different context. So once this is completed, the participant, we extract for each individuals, we use these subject-specific ROIs as their sort of localizers. And from that, we calculate Pearson correlations of regions, these functional ROIs that are extracted, and look at connectivity between these regions for rest as well as for story listening. So we end up with this matrix where we're looking at functional ROI to functional ROI connectivity matrix, not anatomical. And now we get a matrix that allows us to look at where there's functional activation within the language network within the MD network and across network. So we're specifically focused on looking at hemispheric level connectivity, where we're looking specifically at left hemisphere connectivity, right hemisphere connectivity, interhemispheric connectivity in the language network, as well as looking at within the network, as well as in the MD network, within MD network connectivity and inter-network connectivity. So what you see in the results here are essentially comparisons of connectivity between controls and patients, and then between language to language connectivity, language to multiple demand, and within multiple demand connectivity, as well as only in the left hemisphere, only in the right hemisphere, and between hemispheres. And at rest first, what we have found is after a stroke in patients with aphasia, there's disrupted connectivity within the left hemisphere. There's also no increased connectivity within the MD network, as you see at the bottom here. They're worse off than controls, and they don't show any more connectivity. And also they don't show any connectivity, increased connectivity between the two networks. This is at rest, and we get exactly the same results during the story listening task. The only thing that's interesting is there's higher within network connectivity slightly in both these tasks for the patients here. So while we set out to find out if patients with aphasia recruit MD regions as a compensatory mechanism to process language after a stroke, we didn't find any evidence of that in this study so far. This is a bigger project, and I'll have to come back and tell you other parts of that story. So let me move on to the next study, where we're looking at cortical activation for naturalistic discourse. In this case, we're looking at real-time conversations as well as watching videos using functional near-infrared spectroscopy, or fNIRS. We're doing this in healthy individuals as well as in individuals with post-stroke aphasia to provide ecologically valid insights into the neural mechanisms that support discourse, and of course how they change after brain damage. So for those of you who don't know what fNIRS is about, it is essentially a methodology that uses near-infrared light to measure hemodynamic response and task-based cortical activation. So this is on the surface of the brain, and these optodes have a light source and an optical detector that essentially captures that blood flow. There are many benefits for fNIRS, including the greater temporal sensitivity, as well as the fact that you can do this with people sitting in the lab right in front of you. Since we are looking at language processing, we're interested in the language network, so we've designed an optode cap that involves specific brain regions that are involved in language in both hemispheres, that includes 37 channels and 8 short separate detectors. These are 3D printed caps in-house, and then for every subject we take head measurements to know exactly where to put it. Once we collect the data, we manually exclude blocks with error or no responses. We exclude channels with lesion tissue. We prune channels with low signal to noise ratio. We transform the data, we correct it for motion, and then we estimate hemodynamic response function using GLM. So the task itself here is the cloudy video I showed you earlier, except here they're watching 68 seconds of the video, then the video pauses, and then they have to summarize what they see. And then again, they watch 60 seconds, and they have to summarize it. The order of these are they sort of goes in a sequence. In the control condition, they are watching scapes, a silent video for a while, and then they have to count from 1 to 15. The participants in this project include 14 young adults, 15 age-matched adults, and 17 individuals with post-stroke aphasia. And so the age-matched older adults and post-stroke aphasic patients are matched, and they're generally distributed in. I'm going to show you data for the three groups differently. So these are young neurotypical adults. I just want to orient you first here for every one of the ROIs we're looking at that I showed you before. We're looking at the data over time. So on the x-axis, you have about 20 seconds of this person's response. What's in bold is their production, their discourse of the video, and what's in dotted is their counting output. On the y-axis is the HBO concentration units. And so we look at each hemisphere, and these are linear mixed effects models over time. So what you can see here is both in the left MFG as well as bilateral frontal regions, there's a clear effect of summary tasks relative to the counting task, the control condition. There's also an effect in the left temporal region, which happens a bit later, as well as in the right precentral region. So this is all for young, healthy adults. Then when we look at age-matched controls, these are healthy older adults, we see a similar and significant difference essentially in all ROIs we're looking at, including left MFG, bilateral frontal regions, bilateral temporal regions, left parietal and right parietal, bilateral parietal regions, as well as bilateral precentral regions, which is a bit surprising. We didn't expect the results to look this different, and I'm happy to come back to it later. And then finally, which is our group of interest, are the 17 patients with aphasia. And again, here we find significant differences between the summary, the discourse task relative to the counting condition over time in left MFG, bilateral frontal regions, right temporal region, right parietal region, and surprisingly, we find a different effect, an opposite effect in left parietal regions for these individuals. Just to summarize all these, because I showed you a lot of results, essentially what we find is that the left MFG is involved in is active for all three groups, greater for the summary. Left precentral is only active for the age match groups. Left frontal is active for all three groups. And right frontal is active for all three groups. Left temporal and right temporal are active for the age match as well as for patients. And then we find some interesting differences in left parietal regions. And we find differences in right precentral for summary greater than counting again. So again, very important setting the stage for us with our patients, because we're able to show a clear response for discourse relative to counting, both in our patients as well as our age match controls. In conclusion, at least for this project, what we find is that fNIRS, we get good condition effects. There's greater activity in bilateral frontotemporal ROIs for experimental versus control conditions. We get some condition by condition effects in the control ROIs. We get greater activation in the young healthy adults relative to age match in individuals with aphasia. But this idea of we get this clear bilateral frontotemporal activation in the young patients and adults. Where we're going with this really is to use these paradigms to understand naturalistic language networks that can change as a function of rehabilitation, and using fNIRS and naturalistic paradigms to actually measure the language outcome itself instead of staunch behavioral measures. So I'm happy to talk about that as well.